Today, in every home, commercial, and industrial building, there's AC power that supplies all of the required power for anything from charging a cell phone to the appliances in your kitchen or even the car now that's charging in your garage. Traditionally, electrical endpoints like outlets, switches, circuit breakers in these buildings are nothing more than passive devices that power things on and off downstream. These devices, though, are in a perfect position to do so much more than just supply power. They have an access to unlimited energy source, and they can provide a whole host of control and feature functions. The challenge is the AC grid is an extremely hostile environment, with all sorts of fluctuations in voltage and in current from either the utility company or solar that might be on the roof to the downstream appliances and motors. These fluctuations in combination with high heat would traditionally be catastrophic to any solid-state device that is controlling power. But today, you will see that this is no longer the case. Amber Solutions' breakthroughs in solid-state architecture solve the major problem of survivability in these extremely hostile environments, and can do it from a much smaller silicon form factor. Using traditional, off-the-shelf Infineon silicon MOSFETs, Amber can control the power downstream to the load in a completely solid-state architecture, and provide its own unique proprietary regulated low-voltage DC power to incorporate native intelligence that provides advantages of energy awareness and management. Amber in a silicon architecture not only survives the environment, but creates an indestructible arc-free operation for enhanced safety. It leverages embedded intelligence like software and algorithms to analyze the power and provide protection. This intelligence and safety creates new value for endpoint products in the whole building grid, and in many ways are not possible or reasonably installed today. We're going to be doing two demonstrations. Both are focused on inductive load. First, we'll see how hostile the AC grid can be on electromechanical circuit breakers of today. Second, what we're going to be doing is showing how Amber's completely solid-state technology can not only handle the hostile and challenging inductive load, but it can do it hundreds of times over 15 minutes. Inductance is a common phenomenon. It can come from something as complicated as an AC motor load, or it can be from something as innocent as parasitic inductance created by wires snaking downstream from a circuit breaker. This excessive amount of wiring holds energy after power is switched off upstream. The result is a very powerful kickback of energy that spikes the voltage as it tries to find a way to escape and get back to equilibrium. In our first demonstration, we're actually going to demo how powerful that kickback can be, and we're going to use a traditional circuit breaker here to test this. So what we have here is a normal circuit breaker. Upstream of that device is an AC power source that's providing power to the system, and downstream is an inductive load that's actually providing the energy as it kicks back through the device. We also have an oscilloscope here. It's actually measuring the voltage across the switch as we switch it. Now, inside of the circuit breaker, there are two metal contacts. When those separate, the power from the inductive load is going to shoot back through the device. That's going to spike the voltage so high that the power actually jumps between the contacts and creates an arc as hot as the sun. When this happens, the device is actually going to pass power, and I'm going to be measuring that on this oscilloscope in front of me. So what we're going to do is I'm going to flip the switch, and we're going to measure the voltage as it goes across the switch on the oscilloscope. And this is thousands of volts that are jumping across there. And ultimately, those arcs and those sparks are what hurts the internal componentry of electromechanical devices. It can even weld them shut over time, or it can erode the contacts to a point where they can't even close, creating a catastrophic failure. Some devices even use an arc suppressor for enhanced protection. This is an example of traditional electromechanical switching, but it can be applied to a wide range of other applications. We will now demonstrate how Amber uniquely manages inductive load purely through solid-state technology. In this case, we're using Infineon silicon MOSFETs. In this demo, you'll see Amber's AC switch turning on and off 30 times per minute for a total of 15 minutes. Each time this happens, it represents exactly the same hostile event we saw previously in the last demo, which was shown with the electromechanical circuit breaker. Electromechanical circuit breakers have galvanic isolation, which provides more protection than dielectric isolation that solid-state switches have. Traditionally, solid-state switches could never handle this voltage spike, which can easily hit thousands of volts, only with the dielectric strength itself, until Amber. Amber's demo behind me can recognize the voltage spike through extremely fast sampling and can nearly instantaneously cap this spike through switching before the voltage is able to get too high, causing a catastrophic failure. Without Amber, a solid-state device would fail if subjected to the same conditions as this test. It is operating with significant margin and can even be programmed to adjust the peak voltage independent of the AC mains. In order to prove that this is sustainable, we're running this test 450 times back to back over 15 minutes. What I have here is I have the oscilloscope behind me, and we're actually going to start the test now. So I'm going to run the test. And what you see here is the switches actually turning on and off, and that's what creates this packet train of switching in these little bars. So what we're going to do is I'm going to step away for a few minutes and let this run, and I'll be back at around a 10-minute mark, but as I said, we'll run this for 15 minutes. So we're at about 10 minutes, and as you can see from the oscilloscope that Amber is consistently and evenly clamping the voltage, eliminating potentially any risk or hazardous situation. So I'll be back in about 5 minutes or so to check in again. So we are just hitting the 15-minute mark of consistent switching, and as you can see, there were absolutely no challenges or issues whatsoever. Let's take a closer look at the oscilloscope to see how Amber is managing the inductive load during each one of these switches from on to off. First, what we're going to look at is the line voltage, which is represented by the pink line here. The second was the current, which is actually being measured by this green line. And finally, which is the most important line that we're going to be looking at, is going to be the voltage across the switch, which is represented by this yellow. We're zooming in right now to actually see how high this goes. So as you can see, this spike is only going up to 260 volts. This is extremely different than the electromechanical switch that we had seen. The electromechanical switch was up in the thousands of volts. It would have hit the ceiling if we had it in front of us. This ringing is also extremely limited. As you can see, it returns back to equilibrium quite quickly after that single surge event. The reality is, Amber can capture, manage, and mitigate the surge before it ever becomes an issue. This demo is just one example of the far-reaching implications that silicon-based electrification provides when powered by Amber. Our modern silicon intelligence solves major industry problems and regulatory concerns, opening new opportunities for enhanced features that until now weren't a part of a design engineer's world of the possible. Amber's breakthroughs in the digital management of electricity within a solid-state or silicon architecture does so much more than increase safety, as we saw in this demo. Amber-powered electrical products uniquely integrate modern intelligence, or AI, for such advantages as enhanced energy savings, elimination of AFCI and GFCI nuisance trips, extraction of DC directly from AC mains, and a more dynamic power delivery range than traditional electromechanical solutions. Amber's much smaller silicon chip power management and AC switching architecture with its own embedded electronic thermal management creates new flexibility in cost of goods and space within products. This creates an impressive increase in sensors, control features, and really the overall value within outlets, switches, appliances, and basically anything else that's AC powered. The result is not just smarter electrical products, but dramatically smarter buildings. Amber siliconization of power management into much smaller system-on-chips transforms the electrical product landscape within the electrical grid itself. A true second electrical revolution.